Last time we talked about Lewis structure. Okay, we talk about the Lewis structure in the different conditions. First, the Lewis structure for the single elements. And then you just need to count what is the valence number of the valence electrons for these elements. And then you put the dots on the outside. But for the elements itself, you have to assign single dots on one side first. And then if you have a more, you put more dots. That's for the single elements. So to counting the valence electron is very important. Last time we talked about to know the valence electrons in the main group, you just need to know what is the group number for those each of the elements. Okay, one A group has one valence electrons. And we also talk about Lewis structure for ionic compound. Okay, so ionic compounds, the reason it's called ionic because they have a charge. They have a positive charge and negative charge. The reason they become negative charge and positive charge, that's because, for example, sodium chloride. Sodium only have one electrons, and they prefer to lose one electrons become a noble gas form. So they completely lose the one electrons. And the chlorine gases, this guy needed one more electrons. To want to gain one more electrons, also become argon, noble gas electron configuration. So chlorine gain one electrons completely. So that's why sodium become a one positive charge and chlorine become one negative charge. And then the positive and negative charge attract to each other, making bonds to making ionic compound. Okay, so that is the this is how the ionic compound make the bonds. So that's why when you draw the Lewis structure for the ionic compound, you need to make sure you're gonna have a positive and negative charge shows up there. This just recognize we have a positive and negative charge. But for the molecular compound is different because molecular compounds, they are not going to gain or lose completely the electrons. Instead, they are attract the electrons. They're sharing the electrons between the molecules, between atoms. They're sharing the electrons between the electrons, and those shared electrons making a bonds. Okay, the shared electrons making a bonds. The shared electrons making a bond. If we have a one pair of shared electrons, they have a single bonds, two pairs, then double bonds, three pairs, that's a triple bonds. Okay, so this is how the molecular compound make. They're not a gain or lose electrons. So each of the atoms do not have a charge. Okay, they're sharing electrons. This is the difference, completely difference between the ionic compound and the molecular compound. So that's why we need to talk about how come we can make the correct formula for the molecular compound. You first need to count how many valence electrons for this compound. How many valence electrons? They have 8, 7, 8, 16. And usually, if you count the valence electrons, most of cases is an even number. Okay, most of cases is even number. Or in your test, generally it's all even number. I mean, no odd number. Because for the ionic compound, for the molecular compound, all the molecules pair to each other, all the electrons pair to each other. So those are all paired electrons in the molecular compound. So if it's a paired electrons, so you shouldn't see a lone pair. I mean, single electron shows up there. Those are all paired. So that's why the valence electron you can see those are all even numbers. Okay. And we also talk about how to write the molecular compounds. First, you need to see which one is a central atom, which one is a side atoms. Central atom writing the central. This is only one atom. That definitely is a single atom. That's a central atom. the one has more atoms, that means it's a side atoms. So you put a side atom around it, and each of the atoms will share each other's. Okay, and then you're gonna count how many valence electrons in total for these molecules, and then you're going to assign the dots. We talk about you're going to assign the side atom first. The side atoms either follow the octet or duet. Either has 8 of electrons or 2 of electrons. Hydrogen only have 2 electrons, but for the rest of others molecules, for the other atoms, those are all 8 electrons. Okay, so assign the dots on the side first. When those fulfill the dots, and then you start to adding dots inside for the central atoms. And we also talk about for the molecular, for the polyatomic ion, they're doing the same thing. You still can you can also assign the dots, but in this case, what you do, you need to count valence electrons inside of molecule. Also, you need to including the charge. Okay, the charge also including in the number of the valence electrons. For example, NO3 minus. If you're just counting the NO3, they only have a 23 valence electrons. But since they gain 1 electrons, become a negative charge, so you can count 1 negative charge to become 24 valence electrons. Okay, yeah, so if this is negative charge, you gain electrons. If you're as a positive charge, you're losing electrons. Okay, and we also talk about some of the exceptions. Okay, the central atom can have more electrons or have less electrons, but none of this, if you're looking at the exception, all the side atoms are follow the octet. Okay, which means the side atoms is always has 80 electrons or 2 electrons. Okay, only the exception is for central atom. The central atom either has more dots or less dots than 8. Okay, either has a less 8 electrons or more electrons in the central, but the side atoms always follow the octet. Okay, and also we talk about if you have extra dots, you need to assign. You need to make sure you're gonna assign in the central atom, and each of the dots should be paired. If you have 4 dots extra, then you have 2 pairs. If you have 1 dots extra, then you have just 1 paired electrons. Do not put the dots separately around the central atom. And we also talk about the formal charge. Okay, formal charge is not helping you to figure out the charge. It's help you to figure out which formula could be the correct formula. Okay, which formula could be the correct formula. So the basic rule is the more zero for the formal charge, the better the formula will be. Okay, you're gonna find the one has more zeros. You're gonna find the one that has more zeros. Okay, that is for the formal charge. Okay, and also last time we did some of the practice, and today we'll continue to talk about those some left over. First thing we're going to talk about is the polarity of covalent bond. The polarity of the covalent bond. So first of all, let's talk about what is the polarity. So what do you think? What is the polarity mean? Polarity, polar. What is the polar mean? Charge what? Yeah, in this case, yes. The charge, we have a separation. for positive and negative, that is the polarity mean. Well, polarity in general, you will talk about temperature polarity. So that's why we have North Pole, South Pole, and equator. Okay, yeah. So that whole polarity in this case is talk about temperature separation, right? The polar North Pole, South Pole really cold, and temperature in the equator is really hot. Okay, so that is a temperature separation. And we also has a magnetic polar, right? Polarity. That means we have a south and the north pole separately. Okay, yeah. So separation here is the polarity. The polarity of the bond over here is talk about in this bond we have a separation of a positive charge and a negative charge. Okay, so this is the polarity mean. Okay, so let's see what happens. So first we see a situation that do not have a polarity. Okay, which means we do not have a positive charge and negative charge separation. Okay, and again, this is talk about the covalent bond, which is not talk about ionic bond. If we talk about ionic bond, they always has a polarity and extreme the polarity, because sodium ion and the chloride ion, they already have a positive charge and negative charge, right? So in this molecule, you already find one positive end and one negative end. That makes sense, right? So we're not counting the ionic compound. We're talking about the covalent compound or molecular compound. We're not talking about ionic. Instead, we're talking about the molecular bond or covalent bond. So first, let's see some of the situation. This is the example that we are talking about. The reason the two hydrogen can make a bond because they are sharing the electrons, right? They are sharing electrons. But just let you know, the electrons in the middle here is not just it's not moving. It's not just stay there forever. It's kinetically static, which means they're stay here, but it vibrates. Why? Just like think about the tug of war. One side people over there, the other side over here, you have a little flag in the middle, and the people is pulling the rope. Okay, so even the flag is right in the middle, it doesn't mean the flag is not going to move. It could move here, it could move there. It's not moving because the force on both sides are equal. It makes sense, right? Yeah. So the shared electron is in the same thing. The hydrogen, this hydrogen is going to pull the electrons over there. This hydrogen also going to pull the electrons on the other side. Since both are hydrogen atoms, they are equal, right? So even the force they pulling is different, it's the same. So that's why the two electrons share electrons right in the middle. So in this case, those two electrons are be shared is equally, right? The electrons shared equally. The electrons shared equally, so that is why we're going to no charge or no difference on both sides. Okay, so that's why in this case we call this is a non-polar. The shared electrons making this bonds, and so that's why we call this bonds is a non-polar bond, because this bond is not belong to, I mean, it's a 50-50 shared between atoms. That makes sense, right? So in this case, it's called a non-polar bonds because they're sharing almost equal, or very identical, because those two are the same thing. Okay, yeah. But the force they're pulling this parts is called electronegativity. And remember, when we talk about the periodic trend, we talk about electronegativity. electron negativity. Electron negativity is shows the muscles between molecules, right? It shows the muscle between to pulling those electrons. Okay, so this guy is identical, so that's why we have a polar bond. And if you're talking about the fluorine, and we have another fluorine is doing the same thing. Although this fluorine has a lot of dots around it, but they're still just sharing the 2 electrons in the middle. And since those two are identical, so each of the fluorine are shared exactly the same for the shared electrons. So the bonds they are making is also a non-polar bond. Okay, so this is also a non-polar bond. This is also a non-polar bond. Okay, make sure this is also a non-polar bond. But not always is having something like that. If you have a hydrogen and a fluorine, putting that together, then the shared electrons in the middle, this is a Lewis structure for HF. And then here, this shared electrons is not in the middle because the electron negativity between fluorine and hydrogen is different. And when we talk about the trends for the electron activity, we talk about this area has the very highest electron activity. Remember, right? And this area has the lowest electron activity. Hydrogen is over there. Well, it's much lower. It's much smaller than the fluorine. So what happens? The electrons in the middle is going to pull the fluorine is going to has a much force to pull the electrons than the hydrogen. Okay, so in this case, well, remember this is just pulling the electrons. It doesn't mean we're going to gain these electrons. Okay, yeah, they are sheer electrons. They are still sheer electrons. If you talk about fluorine, the electrons is a 50-50 shared. Maybe in this case, it's not 50-50 shared. Probably it will go like this. Maybe this is a 10-90% share. Do you understand what I'm talking about? I'm just to give you an example. Maybe not exactly the same, but this is probably the case. Okay, hydrogen gonna share less, but the fluorine will share more. So the electrons is going to move close to the fluorine, but not completely gained by fluorine. Okay. So in this case, you will see a trend. Okay, you will see a trend. The electrons is going to moving to the fluorine side. Okay, and remember, fluorine is share more of this. One of the dots is belong to fluorine itself, but there's another dots that's move close to fluorine. And remember, this one dots, if the fluorine completely gain the electrons, then the fluorine will have one negative charge. That makes sense, right? But this guy is not completely gain, but they're having probably 90% share on these electrons, which means this guy will have a little bit more negative charge, right? Maybe it's not exactly one negative charge. Then maybe they have like a 0.9 negative charge, but not exactly one, -1, okay? And then the hydrogen side, maybe since they are losing partial of the electrons, so they may have a positive 1.9. This guy is a 0.9. Although the hydrogen is not completely gained by the fluorine, but the fluorine side, they more or less has negative charge over here. So that's in this case, the charge is separated. Hydrogen end has a more positive charge. Fluorine end has more negative charge. And then the electrons is moving from middle to the fluorine side. And then if you're looking at the whole molecules, you will see this side, on the fluorine side, they have a partial negative. On the hydrogen side, they have a partial positive. So this sign means a partial. This is a partial positive. Partial negative and partial positive. So this is what happens. Okay, yeah. So that's why the polarity is coming out. When this guy share the electrons, become HF, and then you will see the fluorine side will be so these bonds were generated. That's become a polar bond. This guy is a polar bond instead of non-polar bond. Are you clear? Okay. So this is the difference between polar bond and non-polar bond. Okay. Difference between polar bond and the non-polar bond. Okay. So, but the point is, how can we determine, for example, if we have HCl and HF? So this guy, you see, those are all polar bonds, because most of the case, those two molecules are different. Okay. Now, so those are all polar bonds. But the point is, which one is bigger? Which one is more polar? Which one is more polar? That's gonna be a question. How can we determine which one is more polar? Then that's gonna be coming from the idea. Okay, how do we count the electron activity? How do we determine the polarity? How do we determine the polarity? Usually, we need to determine the polarity, we need to find the electron activity between each others. We need to find the difference of the electron activity. Okay, we need to find the difference between the electron activity. Let me just find one of the examples. Okay, electron activity. Let's see. Fluorine is a 4.0, chlorine is 3.0, hydrogen is a 2.1. So if you're talking about the electron activity, and then here we said hydrogen electron activity, they got a value is 2.1. And the chlorine, the value is 3.0, and the fluorine value is 4.0. Okay, to figure out the electron activity, the bond, the polarity of the bond, the people usually to figure out the difference of the electron activity, which means the difference between these two bonds. For example, for the HCl, the bonds, how do we calculate? Which is the difference, the absolute value. So the difference between chlorine and hydrogen. Hydrogen is 2.1, subtract 3.0. This is difference. And we're putting this, means this is the absolute value, which means always is a positive one. Also always positive. So 2.1 minus 3.0, this gives you a 0.9 for the electron difference of the electron activity. And H and F, this also the difference is a 0.1 minus 4.0. This is give you a 1.9. So you figure out the difference of electron activity. the higher number, the bigger, the more polar. Okay, the higher number means more polar. So if you're talk about which polarity, which one is more polar for the bonds between hydrogen and chlorine or hydrogen and fluorine, if you're looking at here, hydrogen and fluorine is more polar than the hydrogen and chlorine bonds. Okay, so this is talking about the polarity between the polarity of each of the others. Okay, so usually the people, how do we determine this? The people, scientists give us a range between this. If the change of the electronegativity between 0 to 0.4, then we think this is a nonpolar bond. This is a nonpolar bond. Okay, for example, the hydrogen bonds, since those hydrogen both are 2.1, so definitely the difference of electronegativity is 0. So this guy is a nonpolar. And the other cases could be carbon and hydrogen, And if you look at here, carbon is 2.5, hydrogen is 2.1. So 2.5 for carbon, 2.1 for hydrogen. So the difference between this, you can see the difference is 2.5 minus 2.1, and it give you a number is 0.4. So the 0.4 is in the range of this. So that's why the carbon and hydrogen bond is also a nonpolar bond, although those two are different. Okay, although those molecules are the compound, the atoms are different, but they do belong to a nonpolar bond. Okay. And if you have a 0.4 to 2, then this gives you a polar bond. This gives you a polar bond. Okay, just like the H and F. This guy is a polar bond. HCl is also a polar bond. Okay, so in this case. So if you have anything larger than 2, generally this is an ionic bond, which means this is belong to the ionic compound. It's not a molecular compound anymore. Okay, this is not a molecular compound anymore. This is a ionic compound. Okay, so this is the range talk about nonpolar and polar, polar and nonpolar. Okay, polar and nonpolar. But the point is, in the exam, we're not going to give you what is the electronegativity number for each of the elements. But how can we determine what is the bonds, the strength of the bond or polarity of the bond between each of the molecules? Okay, this is, again, you're still thinking about the difference of the electronegativity, but we're talking about the trends over here. The difference in electronegativity, but we're talking about trends. So please pick out your study guide. Let's look at the page 17. Page 17. Page 17. And you can see the question number 4 over there, page 17. Question number 4. And you can see which is the most polar bond. Which one is the most polar bond between carbon-carbon and carbon-hydrogen? What do you think? Okay, carbon and carbon bonds and carbon-hydrogen bond, both are non-polar bonds. But which one is a little bit more polar? Carbon-hydrogen. Because you are looking for the difference of electronegativity, right? Carbon-carbon, both are the same. So the difference of electronegativity is 0, right? The carbon-hydrogen, the carbon is over here, hydrogen is there. So they are having different electronegativity. So the difference definitely is bigger than 0. That makes sense, right? So that is why carbon hydrogen should be a little bit more polar than the carbon-carbon. Although both are belong to non-polar polymer, but the carbon hydrogen is a little bit polar. The polar here is talking about separation. Okay, the carbon, the positive charge and negative charge is a little bit different, separate than the carbon and the carbon. Are you clear? Make sense? Okay. Okay, so the next one is nitrogen and hydrogen, and oxygen and hydrogen. Remember the trends. We talk about this. Here is the biggest. This here is smallest. In another word, they are including two trends. From top to the bottom is getting smaller. From right to the left is getting smaller for the electron activity. So here, nitrogen and hydrogen, and oxygen and hydrogen. Okay, think about how the change of the electron activity will change. Remember, the trends is go. This is a smaller. This is smaller. And remember, hydrogen is over here. Nitrogen is here. Oxygen is over here. So what do you think? What is the difference? If you're talking about electronegativity, is the hydrogen has a fixed value. If you're not sure how to do this, then at least you can make up some numbers, right? If the hydrogen is 1, what do you think? Is nitrogen bigger than 1 or smaller than 1? What? If hydrogen is 1 value on the electronegativity, is nitrogen bigger or smaller than 1? It should be bigger, right? Because the trends, look at it here. On the left side is getting smaller, right? So you can mark this guy as 2, right? Then what do you think? Nitrogen and oxygen, which one is bigger? Is nitrogen bigger or oxygen is bigger? Oxygen is bigger. Then you can see this is 3. And then tell me which one got a bigger number. This guy is 2 and this is 1. This is 3 and this is 1. Which one has a bigger difference? Oxygen and hydrogen. Okay, so if the question don't give you the number, you can just make a number. Okay, but at least you're gonna follow the trends over here. You're gonna follow the trends. So that's why oxygen and hydrogen will have a hard polar. It's the most polar bond between those two. It's more polar. Do you understand? Clear? Okay, then how about next one? Hydrogen and fluorine, and hydrogen and HCl. I think we already talked about this. Hydrogen and fluorine is bigger than hydrogen chlorine. So let's look at the next one. Oxygen, nitrogen and oxygen bond, and a carbon oxygen bond. What do you think? Carbon is shows over here. So here is talk about is the carbon oxygen, nitrogen oxygen, which one is bigger? Then again, if you want to talk about the numbers, you can just mark between carbon, nitrogen, oxygen, which one is the smallest? Carbon should be the smallest because the trends, look at the trends. On the left side is smaller. So carbon is smallest. So the carbon, you can assume this is 1. Nitrogen is bigger than carbon.
but it's smaller than oxygen. So you write this 2. Oxygen should be biggest number between those. You can write 3. So here, this is 2 and 3, and this is 1 and 3. The difference between here, this is 1 difference, and this is 2. So which one has a bigger polarity? Obviously, carbon and oxygen will have a bigger polarity. Okay, so go ahead to work on the hydrogen and the sulfur, oxygen, and hydrogen. Okay, so please figure out which one is bigger than this one. Please just go to finish the CDE. Okay, CDE. Based on the trends for the electronegativity. Those two molecules are more far away, means they have a bigger, the higher electronegativity, the difference of the electronegativity. Okay, go ahead to work on the CDE. Go ahead and work on the CDE. Okay, so in this case, sulfur, where's the sulfur? Sulfur is in the bottom parts of the oxygen. Okay, so again, difference between sulfur and oxygen. What do you think? Hydrogen is over here, sulfur is over here. So oxygen and sulfur, which one is bigger? Sulfur bigger or oxygen bigger for electronegativity? Oxygen is bigger. So you can just say this guy, well, sulfur is 2, and this is 3. And you can just assume this is 1. It really doesn't matter. This is 1, this is 1, hydrogen is 3, sulfur is 2. Which one gonna be a bigger difference? Okay, obviously oxygen and hydrogen has the bigger difference. That makes sense, right? Okay, yeah, so this is how you're determining phosphor and the chlorine, sulfur and the chlorine. Okay, again, this is the same thing. Okay, where is the phosphor? Phosphor is over here. Okay, between phosphor and the chlorine is right over here. Chlorine is right over here. So between phosphor, sulfur, chlorine has the biggest number. So phosphor has the smallest because you look at the trends. Okay, the trends we talk about, this area is biggest. Okay, they determine separate the two directions. From left side has the smallest, right side has biggest. So phosphor should be the smallest between phosphor, sulfur, and chlorine, right? So you can assume phosphor is just 1, sulfur is 2, chlorine 3. And if you put over here, this is 1, 3, this is a 2, 3. So which one has the bigger difference? Obviously, this one has the bigger difference. Make sense, right? The next one, carbon and hydrogen, nitrogen and hydrogen is doing the same thing. Okay.
carbon and nitrogen. Carbon is smaller than nitrogen. So you can count this guy is 1, this is 2. Really doesn't matter what is the hydrogen. So carbon is 1, nitrogen is 2. This is a fixed number. So which one give you the bigger difference? So obviously this one give you a bigger difference. That makes sense, right? Okay, so this is how you determine the polarity of the bonds. Okay, polarity of the bonds. All right, so let's take a break, a small break. Okay, so the next part we're going to talk about the shape of the molecule or the geometry of the molecules. The molecule, they do form a shape. Okay, the different molecule, different the Lewis structure give you the different shape. Okay, so first let's look at one of the demos. So probably you already heard this before, but we're going to looking at again.
as balloons. So we have tells us that the electron pairs will try to get as far away from each other as possible, and so we can use these balloons to figure out what those shapes would be. So some atoms and molecules have 2 electron pairs around the center atom, and if we tie then 2 balloons together and look what shape those make, we can see that they make a straight line. They're right across from each other, 180-degree bond angle. However, if we take 3 pairs, 3 balloons, and tie them together, you can see that this is the arrangement that we get. I'm not making them into that, that's just kind of the natural lowest energy state that they can go into. So in this, you have, imagine that the atom is at the center, you have these are electron pairs around it, and you have 120-degree bond angles, and it's flat.
Okay, so just to let you know, the reason they are using blue is because the electrons is much bigger than the nuclear, right? So the electrons occupy as a much bigger space, just like a balloon. But the electron and the other side electrons, they're going to push into each other's, right? So they have the same charge, so they will repel to each other's. So that's why if you have a different number of size of this electron cloud, and then they are going to initially to form different shape because those electron cloud are going to pushing the different molecules, different atoms to the side. You understand? Does it make sense, right? Yeah. So the electron cloud is pushing those stuff to each other, again, against each other. So that's why they initially, because we have a different number of those electron clouds, they are going to shape the different shapes. Okay, yeah. So
this structure, that last one is called linear. This structure is called trigonal because it's got 3 sides, but planar because it's flat. Trigonal planar. If we then go ahead and throw a 4th pair on there, not easy to do. There we go. We can see that they take this sort of, it's almost like a tripod arrangement where you have each of the pairs is sort of, if you look at these real closely, these balloons are not flat, they're pointing down a little bit. Down, 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 just a little bit, and this one's going straight up over the top. This is called a tetrahedral, named so because it has 4 faces. Tetra, 4, hedra, face, faces, I guess. Tetrahedron is the singular. So you have 1 face, you have like a, think of it kind of like a pyramid. I don't want to say that too much because there are other things we call pyramids. This is a tetrahedron, but you have 4 faces. You have a face here, 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 and on the bottom. The bond angle here is bond angles here are not easy to necessarily visualize, but you can tell that they're more than 90 degrees, but not as much as 120. It turns out that the number is 109.5, and so those are the basic arrangements for electron pairs around the central atom in Chem 1 for 2, 3, and 4.
okay, so this is the generally is what the looks like. This is the geometry of the molecules. Okay, so I will only focus on, I mean, if we have 1 balloon, no, I mean 1 balloon. If we have 2 balloons, 3 balloons, and 4 balloons. So of course, if we adding 5 balloons and 6 balloons, so naturally, at least the maximum they can have like 4 balloons or 6 balloons altogether to make octahedral shape.
Okay, yeah, but I will only focus on 2, 3, and 4. Okay, 2, 3, and 4, and talk about the variation of those 2, 3, 4. Okay. So the balloons in here. So this model is called a VSEPR model. Okay, VSEPR model. V is called the valence shell. This is valence shell electron. Valence shell electron pair repulsion. Valence shell electron repulsion. Okay, valence shell generally talk about the shell in the atoms outside of the electrons, and the electron pair repulsion. So that's why they call the VSEPR. Okay, VSEPR model. So generally we're talking about balloon. So what exactly the balloon shows here? The balloon is what we call the electron domain. This is called the electron domain. Electron domain. So different molecule, the central molecules may have a different electron domain. So what exactly the electron domain shows here? The electron domain, valence shell, that's count the electron domain. The electron pair also count the electron domain. So let's just looking at one of the case like this, methane. Methane, the central carbon has a 4 electron bond, 4 bonds, single bonds over here. And they have 4 single bonds. Each of the single bonds count as an electron domain. So this guy has a 4 electron domain. This guy has a 4 electron domain. And if we say, okay, so ammonia, NH3. Ammonia, if you draw the Lewis structure, that's going to be the Lewis structure for ammonia, which is N3, NH3. That's ammonia. And ammonia, if you're looking here, they have a 3 bonds, and also they're having 1 lone pair, and each of this also count 1 electron domain. So this guy also has a 4 electron domain. So here, then you will see, doesn't matter if it's single bonds or electron lone pair, those are all count electron domain. Yeah, the lone pairs actually has a much bigger size than the bond. Okay, than the bonds. They have a bigger cloud, electron cloud than the bonds. Or you can see something like that. This is also one of the bonds. This is called hydroaldehyde. This is called hydroaldehyde. So this guy, if you're talking about central atoms, they have a 1 double bonds and 2 single bonds shows over here. And then this guy, again, double bonds only count 1 electron domain. So this guy only have a 3 electron domain instead of 4. Double bonds and the triple bonds all count 1 electron domain. So this is one case. You see, they have 2 single bonds and 1 double bonds. Then this guy, the central atom carbon here, containing 3 electron domain instead of 4 electron domain. Okay. If you're talking about this guy, this is called alkyl. The alkyl over here, if you're talking about this atom, this carbon,
this carbon, they containing only 2 electron domain, 1 single bonds and 1 triple bonds. So triple bonds, double bonds, single bonds, they'll all count as 1 electron domain. So this guy, the central atom here, this carbon containing 2 electron domain. Okay, yeah. So I need to hope you're gonna recognize, okay, the different electron domain. Counting different electron domain is very, very important. Without that, you will not be able to recognize what's the geometry of these molecules. Okay, counting the electron domain. But the point is, you have to draw the Lewis structure first, right? And then you count the electron domain. So PCl3. Last time we draw the PCl3. What is the Lewis structure for the PCl3? We did that, right? You first count the valence electrons. How many we have? P has 5. 7 times 3. Totally, you have 26 valence electrons. So we put the P in the middle. Chlorine on the side. And then put those shared electrons in the middle. And then to assign the dots on the chlorine first. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And we have 2 more to go, so the 2 more should be in the middle. So now you can see everything should follow the octet over here. And then you will see, okay, so what is how many electron domain that the phosphor containing over here? How many electron domain the phosphor has? How many? 4, right? So they have 3 single bonds and 1 lone pairs. Don't forget the lone pairs. So this guy do have 3 electron domain, 4 electron domain over here. So this guy has a 4 electron domain. Okay, so this is how we count the electron domain. Remember, single bonds, double bonds, triple bonds, and electron lone pairs. Counts 1 electron domain. Okay, so this is how we count the electron domains. So once you know the electron domain, generally you will recognize what is the electron domain geometry. You will recognize what is the electron domain geometry. Okay, what is the electron domain geometry? So if we have 2 electron domain, then generally it's shaped like this. So central atom in the middle. So if you link them together, this is just a linear geometry. Okay, so this is a linear. Sorry, not right like this. This is a linear. If you have 2 electron domains, then the geometry is a linear. If you have a 3 electron domain, then the shape is something like that. So if you're doing the central atoms and the side, it will become like this. So here we have a model over here. If you have a 3 electron domain, generally it's shaped like this. And this shape is called a trigonal planar. Okay, it's a trigonal. And also those 4 atoms are in the same plane. So that's why it's called a trigonal planar. Okay, so this is called a trigonal planar. This is called a trigonal planar. And if you have a 4 electron domain,
if you have 4 electron domain,
then this is called a tetrahedral. So if we have a 4 electron domain, the geometry like this, they have a tripod in the bottom and 1 stick up. Okay, so this is called a tetrahedral. Okay. So this is called the tetrahedral. And of course, we do have a 5 and a 6 electron domain shows over here. I just give you the name. 5, if you have a 5, then the geometry is going to be looks like this. Okay, this is called a trigonal bipyramidal. The trigonal bipyramidal. The reason is they are having three in the middle. So it looks like it's a one pyramid on the top, the other one pyramid on the bottom. So that's why they call the bipyramid. One is the stick up, one is a stick down. Okay, so this is called a trigonal bipyramidal. So if you have a 5 electron domain, then that's called a trigonal bipyramidal. Yeah, trigonal bipyramidal. If you have a 6, then this is a maximum shape. You will see actually this is also the 2 pyramid, but this is a 2-4 pyramid, 4H pyramid. Okay, one is go top, one is go down. So generally, this is what we call the octahedral. Octa means 8, hedral means face. So octahedral has 8 faces. Top they have 8, 4, and the bottom also has a 4. So this is called the octahedral. Octahedral. So generally, you have a 6 kind of the 5 different kind of the electron domain geometry shows over here. But I'm going to just focus on the first one, third one, and the fourth one. Okay, I kind of like don't emphasize the 5 and 6. As long as you do 2, 3, 4, you can remember that's gonna be great. Okay, so for now we know the electron domain.
then we're going to talk about the exactly geometry shape of this, the geometry of the molecules. Okay, the geometry of the molecules. So I'm going to draw a table like this. So first one is a number of electron domain. And then that's going to be electron domain geometry. Then we have we need to count number of bonding domain. Number of lone pairs.
and is the molecule molecular geometry. Formula. Bond angle. And example. Okay, so first, let's just talk about two electron domain. Generally, two electron domain is pretty straightforward. It just has one options. So okay, so if we have a two electron domain, the geometry will be just a linear structure. It's just a linear. So if you're looking at here, this guy, if we have only two electron domains, so they always is a linear. Okay, we have a central atom. Okay, remember, they always talk about central atom. How many electron domain is based on the central atom? It's not based on the side atoms. Okay, you need to count how many electron domain is for the central atoms. Are you clear? Okay, so this central atom, this guy has a two electrons, two bonds, so they are going to just be a linear shape. Okay, so if we have a two electron domain, that's a linear. Here we're talking about the bonding domain or lone pairs. So that means this guy, so the one side, this two electron domain could be just a bond. Bonding domain means single bond, double bond, triple bonds. Okay, those are all kind of one bonding domain. So this guy could be single bonds, right? Then they could also be double bonds, which is still the same shape, or they could be triple bonds. Again, still be the same shape, right? Yeah. So this guy doesn't matter if you have a single bonds, the bonding domain, generally the shape is the same. But they can also be a lone pairs over here. But just let her know, the reason the lone pair and the bonding domain is different is because the lone pairs is other than the bonds. Bond is visible. You can see the bonds. But the lone pairs is invisible. They only have electrons. It's too small to see. So they occupy the space, but you cannot see these parts. So in this case, you're going to missing some of the parts. Okay, so that's why if you have a lone pairs, the geometry could be different. But for the two electron, the two only if you only have two electron domain, it really doesn't matter. Okay. So if we have two bonding domain and low lone pairs, the geometry is still a linear shape. So in general, if you only have two lone pairs, two electron domain, this only just a linear shape. The formula you can just write AX2. AX2. The A is a central atom, X is the side atoms. So that means that they have a one central atom and two side atoms. And if you're talking about the bond angle is 180 degrees. So what that mean? What is the bond angle shows over here? That is the bond angle, which means talk about the angle between two bonds. Okay, so the bond angle is between the angle between two bonds. So this bond angle is 180. Make sense, right? Okay, 180. Okay, so then that's one of the examples. You can see the CO2. CO2, the Lewis structure is something like that. So this is CO2. You see, this is a straight line. Carbon central atom only have two double bonds. then they only have a 2 electron domain. So the geometry is just exactly as a straight line. Okay, it's a linear shape. If you're talking about, then we're going to talk about a little bit complicated, which is the electron domain. So for if we have 3 electron domain, then we know this is going to be a trigonal planar. A trigonal planar. So if we have a trigonal planar, which is something like that, okay, something like that. So if every electron domain are bonding domain, so if this guy only have a 3 electron domain are bonding domain, and there's no lone pairs over here, which is just like this. This guy have a 3 single bonds, right? Then that's gonna be the molecular geometry, which is just like this. And this is also called a trigonal planar. And if you talk about formula, it's going to be just a AX3. Okay, 1 central atom, 3 side atoms. The bond angle, which is straightforward, you got a 120 bond angle, right? Okay, so you have a 360 for the whole degree divided by 3. Then each of this is 120. Okay, because those are equally shared. Okay, so the bond angle here is just 120. One of the example is just a BF3. So this guy is just a 3 electron domain. So you see the boron inside, they only have 3 bonds. So they are just a tetrahedral shape. Oh, sorry, trigonal planar shape. BF3. But so if we talk about 3 electron domain, they gonna have a variation, which means we may have only 2 bonding domain, but one of this instead of bonding domain, but we're going to become lone pairs over here. So again, we talk about lone pairs is invisible, which means although this guy is occupied space, but it's not seen. But the rest of this is not trigonal planar anymore. It becomes a new shape, right? Although this guy occupies space, but there become a new shape. And this new shape is called a band. It's called a band shape. So this is a band shape. There's no more trigonal planar, but a band shape. Any questions? Okay. So that's why if this compound has a lone pair, the geometry could be different. So in this case, if we only have 2 lone pairs, 2 bonding domain, which is 2 bonds, shows over here, and 1 is lone pairs, then the geometry, molecule geometry, gonna be different. It's no more trigonal planar, but it's become a band shape. Okay, just something like that. It become a band shape because this lone pairs is invisible over here. Okay, so if you draw the formula, that's gonna be just AX2E. Okay, so A is still central atom. X means the side atoms. We have 2 side atoms. E, they have 1 lone pairs. Okay, 1 lone pair, electron lone pair. So this is a formula AX2E. Bond angles over here, that's gonna be smaller 120. Okay, the bond angle here is still shows is 120, but just to let you know, suppose technically the electron domain, the lone pairs, since they have 2 electrons over here, so the size usually is bigger than the bond. Okay, so they occupy the bigger space, and this guy will pushing those 2 getting a little bit smaller. Okay, so
this bond angle is a little bit smaller than it's supposed to be. Suppose it's 120, but since we have one lone pairs, and they're pushing the bond angle getting smaller, so we should have a little bit smaller bond angles. I'll give you a real molecules. We can see a real molecules. Okay, so this is SO2. If you see this guy has two double bonds and one lone pairs, two double bonds and two electron domain and one lone pairs. So this geometry is just a band geometry for SO2, and a bond angle is a little bit smaller than it's supposed to be. Okay, suppose we have a 120, but this one is a little bit smaller than 120. Are you clear? Okay, so if we have a lone pairs, then the bond angle should be smaller than it's supposed to be. Okay, so that's why the bond angle is smaller than 120. Okay, one of the example is just SO2. Okay, so that's gonna be the SO2, the geometry. They have 3 electron domains. Now this is a variation for the third electron, 3 electron domains, and then we're talking about the 4 electron domains, and that's it. I'm not going to talk about 5 and 6. 4 electron domains. If you're looking at over here. Four electron domain, this is called a tetrahedral. And this is a 3D structures. So usually draw the 3D structure is hard. And just let you know how do we draw this? You can. This guy has these 3 dots should be in the same plane. And then the other 2, one is sticking out. One is putting in, right? So we can use in wedge and a dash. There's a shape to draw a wedge and a dash to draw the 3D structures. Wedge, this is a wedge. Wedge means is sticking out. Okay, the dash means is sticking in. Okay, so the wedge and dash structures will be the tetrahedral like this. Okay, so if we have 4 electron domain, that's a tetrahedral. If we have 4 bonds, 4 bonding domain, no lone pairs, then the geometry, molecular geometry will be exactly the same, just like the tetrahedral. And the formula will be just AX4. Since we have 4 side atoms, bond angle, if you're looking at here, is a little bit smaller than the 120. This is a 109.5. Okay, 109.5. This is bond angle 109.5. So one of the example is just methane. The methane. They have the carbon has 4 bonds. So methane, this guy is just one of the example methane. This is bond angles, like this. If you're talking about CCl4, they're doing the same thing. Okay, CCl4 means this guy has 4 chlorine. They also has 4 bonds. So this is going to be the tetrahedral. But if we have a lone pairs, okay, although those guys still occupy the 4 electron domain, but remember this guy is missing. So the geometry is no more tetrahedral. It's just a pi bond, right? There's no one stick up. So
this geometry gives you another name. It's called the trigonal pyramidal. We call it trigonal pyramidal. So here, if we have a three bonding domain, and we have one lone pair, and the give us name is called the trigonal pyramidal. Trigonal pyramidal. For the trigonal pyramidal, okay, then that's gonna be just the AX3 E. They have three side atoms and one electron domain. The bond angle, that's gonna be smaller than 109.5. Probably is 107 something. Probably is 107 something. One of the real molecules is just ammonia. Ammonia, they have three hydrogen bonds, hydrogen atom is the bottom, one lone pairs. So that's going to be the geometry. And if you talk about the bond angle here, it is smaller than 109.5. It's about 107.8. Okay, so that's going to be one of the structure like ammonia, NH3. This guy has one lone pairs on the top and the three hydrogens in the bottom. That's ammonia. This is geometry is called the trigonal pyramidal. Trigonal pyramidal. The last one, okay, point there. Last one has two domain. We only have a two bonding domain, and we have two lone pairs. Shows over here. Two bonding domain and two lone pairs, then it's going to be something like that. Okay, so this guy has two lone pairs and also two bonding domain. So remember, the top part here is completely invisible. Although they occupy the space, but completely invisible. And they only have the two bonds shows over here. And this is instead of 3D, they become a 2D structure again. And that's going to be a band structure again. This is a band structure. So if we have a two bonding domain and two lone pairs, and this is just a band structure. Former just AX2E, E2. Since we have two electron domain. The bond angle, that's going to be even smaller than 109.5. This is 104 something, 104 something. One of the example is water. Okay, one of the example is water. So that is why the people drawing the Louis structure for the water is drawing the water is like this. People drawing the Louis structure for water is drawing like this. Okay, the water is a band structures. This is a water. Okay, so water molecules is a band structure. Okay, it's no more 2D structures. Those is water. This guy has two lone pairs shows over there. Okay, yeah, this is a structure for the water. It's a band, and the bond angle here is even smaller, 104.5. Okay, so if you're looking at over here, you will recognize, make a conclusion. The more bond angle, you see, the more lone pairs give you an even smaller bond angle. Why? We talk about the lone pairs is a much bigger occupied space than the bond. So the more they're going to have a bigger space, has a bigger ability to pushing those two angles getting smaller. Okay, so this is the reason. This is the reason. The more lone pairs give you a smaller bond angle between each of the bonds. Okay, the more lone pairs give you bigger bond angles. I'm saying this is because it will be tested. Okay, so very important. Okay, it will be tested. Okay, so this is pretty much I'm going to talk about the variations. The bond angle here is one of the case is mostly popular be tested. Okay, so the more lone pairs, the smaller the bond angle it will be. Okay, yeah. Different the electron domain could be different from the molecular geometry. That's really depends on how many bonding domain, how many lone pairs shows up there. Okay, so if you want to determine what is the geometry of the molecules, you just need to based on those rules. For example, we just draw the Lewis structure for the PCl3. PCl3, this guy has 3 bonding domain and 1 lone pair. And how do we determine what is the geometry of this molecule? First, you see the central atom. This guy has a 4 electron domain, so you go this one. They have 4 electron domain. The electron domain geometry is tetrahedral. And this guy has 3 bonding domain and 1 lone pairs. So they have a 3 bonding domain and 1 lone pairs. So they give us the geometry for this molecule will be the trigonal pyramidal. Will give you the trigonal pyramidals. So the bond angle should be smaller than 109.5. Are you clear? Okay. And if you're talking about, okay, how about this molecule? What is the geometry for this molecule? Then you just need to know how many bonding domain this guy has. Is there any lone pairs for the central atom? They have 3 bonding domains, low lone pairs, which is here, right? Totally, they have 3 electron domain. The carbon central atoms has a 3 electron domain. So this guy should be a trigonal planar geometry. Okay, so this molecule should be a trigonal planar, the geometry. Again, you just need to looking at the central atoms and looking at around how many electron domain, how many lone pairs it has. Then based on the chart, you will determine what is the geometry of these molecules. Any questions? Okay. All right, so we're done for today's we're done for today. And let's take a break and we are going to review the exam 2. Okay, we're going to review the exam 2.